And I'm going to be talking today about some UK case studies about particularly highlighting, as others have done in previous presentations, the particular challenges and opportunities that exist in when doing geological modelling in urban environments compared to from a sort of traditional environment. Okay, so I'm going to pick out 3 challenges and 3 case studies. So the first one is, again, following up with what Jeroen was talking about, how do we predict and quantify artificial ground? This is a particular challenge in urban environments, and I'll show you some work that some of my colleagues have done on that. The next thing, The next thing I'm going to talk about is scale and accuracy. So one of the challenges of working in urban environments, and again, other presentations have picked up on this, is that you're actually demanding a much higher resolution of accuracy of your models. So we think of a traditional hydrocarbon model, sort of an oil field model, that tends to have an accuracy of hundreds of meters, even though, I mean, they're usually working down to 5 kilometers depths. A traditional sort of regional survey model tends to have accuracies of about tens of meters, and that's our experience in the UK. But in that urban environment, you want to get to that plus or minus meters of accuracy, or less if possible. And then finally, I'm going to talk about how we're using 3D modeling to understand interactions of different deposits in the subsurface. Again, this kind of picks up on what other presentations have said. But one of the critical things about trying to do the roles for 3D modeling in an urban environment is actually using that model to understand how different units interact with each other. Okay, so I'm going to use 3 case studies. I'm going to use London to talk about anthropogenic deposits. I'm going to use some work that we've been doing in Glasgow on shallow geothermal to talk about scale and uncertainty. And then finally, I'm going to talk about a place called Grangemouth, which is just between Edinburgh and Glasgow, about halfway between those 2 cities, to talk about understanding link controls on subsidence in that. Okay, so trying to model understanding anthropogenic deposits in London. Now, London is a particularly interesting city because actually the centre of the city, the city of London, the old city of London, actually predates the nation of the UK. It's older than England as a country. So it's been there for a very long time, and a lot of London is built on not natural ground, it's built on other bits of London. So understanding and trying to predict that man-made deposits in London is critical. It's mostly built on other bits of London. The key challenge as geologists coming to try and understand anthropogenic deposits and predict is trying to create stratigraphies in them. Obviously, we're working on quite different timescales, and generally it can be quite confusing. How do you build a stratigraphy in this type of environment? However, so this is the City of London. Again, so this is the study that we're talking about here, I would say, conducted by colleagues. I wasn't involved in this study. The paper is at the bottom there. Absolutely recommend you read it. Is focusing on the very center of the City of London. And what they found is what they used was using materials that you can find and were described in geotechnical boreholes in those engineering deposits to build an event stratigraphy. So using the very simple processes, the same way we build a stratigraphy in natural deposits, you can apply the same thinking to man-made deposits and then use that stratigraphy to try and understand how these deposits vary with thickness and time. So what they found worked very well. They looked at a whole range of deposits, but so a whole range of materials that have been found in boreholes, but what they found worked really well was concrete to pick up the stuff that had happened since the sort of really the 1960s or 50s and 60s. Ash and coal in London was a really good marker of industrial deposits. So this is the Industrial Revolution. So this would be 19th century and 18th century deposits. Brick is an interesting one. Brick has actually been used in London for a very long time, and in fact is actually in some cases as old as Roman. So it's probably not as good a market in London for dating your deposits. In other cities, it might be more useful. And what they found was that, yes, the thicknesses of, when you date your anthropogenic deposits, you can then look at how those thicknesses change with time and with space. They also found that there was a quite strong relationship between the heights of the buildings and the thicknesses of the underlying deposits, and also where we had large over-thickenings of anthropogenic deposits over previous or historical watercourses. So basically, these were areas where we had previous rivers that have been then built on and built over and culverted, and they actually, if you knew where those old watercourses are, that was often some of the thickest deposits of man-made ground. Okay, so moving on, I'm now going to talk about some of the work that I've been involved in. This is in central Glasgow. Many of you have seen the work that we've done in Glasgow over the years, but this is working on a new project, which is a BGS flagship project looking at trying to use trying to de-risk using mine waters as a geothermal asset. So what we had the opportunity to do here, this is part of a larger project called the UK Geo-Energy Observatories. And what we had the opportunity to do here was to site some research boreholes in the centre of Glasgow to try and essentially tap into this mine working to geothermal. As many of you have seen, we have built a huge range of models in Glasgow over many years. Unfortunately, at this site scale, we realised our models were not good enough. So the image we see of the 3D model here is our city scale models, and at this sort of site scale, so the view of the model is about the scale of the aerial photo. There was a lot of noise and variability on that surface, and the model was actually in this case, an accuracy of about 10 or so meters, vertical accuracy. So in this case, we employed some higher resolution modeling software. We used implicit modeling. This is using Skewer GoCAD, but other software, Leapfrog, does similar things to build this much higher resolution model with much more constraining data, and then using the power of the sort of more implicit geological field modeling to produce a much more accurate interpretation of the geology. And of course, the advantage of this is we got to test it. We had the opportunity, because this was obviously for a particular project, we drilled holes into our pre-drilled model and tested its accuracy. And what we found was that, yes, so this little panel in the bottom right, we can see the boreholes that we had drilled, and in the background, the coloured stripes are the pre-drill model, and we actually saw quite good accuracy there. We were usually in about less than a metre, in some cases far better than that. But the two wobbly surfaces that you can see coming through there, they are the old GoCAD surfaces, the old regional city scale model. So again, it gives a feel for, if you're trying to work in that site scale, you do need to start thinking about maybe using different methodologies or things that are a little bit more specific to a site scale. And as I say, we found the implicit methodologies work really well. Okay, so finally, I'm just going to give my final case study is another project that I've been working on in, again, in halfway between Glasgow and Edinburgh, a place called Grangemouth, which sits on the edge of the River Forth. And at that locality, we were interested in the fact that we knew from INSAR data that there was about 30 millimeters of subsidence occurring per year. And if you see in the bottom right-hand corner here, this is the LiDAR terrain model, and you can see these very odd features in the land surface. These don't look natural. They look like mine workings. However, we know that the site, mine workings on the site finished in the 1940s. So the question is, oops, sorry, and also in that area, we have 80 meters of glacial and glacial marine deposits separating rock head from the land surface. So what was going on here? We could see that, that we had what looked like ongoing mine substance, yet the mining finished 80 years ago. And we had a huge thickness of quaternary deposits between them. So again, we used a lot of site geophysics, things like Chimino to improve the rockhead methodology, and a huge suite of EM and other sort of local seismic models to build a really high resolution constrained model here. And this is what we see in this top left-hand corner. And what we also realized was that we looked at the lithological composition of the overlying quaternary deposits and realized we had a huge amount of clay. And based on previous work that had been done on this site, although they hadn't picked up this substance story, we realized that that clay was what's called, what's known in the industry as quick clays. These are glacial marine clays, which are quite famous for being able to landslide in very low angle slopes. There's been some quite significant landslides in Norway that have happened as a result of this. And what we think has happened at this site, and what we could use the model to determine, was that the mine subsidence that had happened in the underlying coal measures had then brought these quick clays into contact with seawater. And this is one of the main trigger mechanisms for destabilization of these deposits, is sort of changing the salinity of them. And it was actually the subsidence that we think might have caused that. Now, what we now know is that this is potentially quite a significant hazard. So all of these areas highlighted in orange here are areas where we know we have coal workings quite close to the surface, and we have mapped marine clays. So we've actually identified a hazard that we didn't even know was there. Probably not actually going to cause a failure like what we see here in Norway. However, if we start to use to do geothermal with trying to use the mine workings below these deposits to do geothermal, there is a potential hazard there, which again we probably wouldn't have recognized unless we had the model to allow us to realize how these things were interacting together. So just in summary, so 3D modeling is critical to understanding urban geology, and accuracy is really quite important for the stakeholders. We found that, particularly trying to get the resolution at the site scale, the implicit methodologies that are sort of becoming more accessible are actually really good at giving that sort of site scale accuracy. And I think what's interesting is that it often requires using traditional geological understanding, like what my colleagues did in London, to understand non-traditional problems like anthropogenic ground. So I hope that's giving you a bit of a flavour of what we've been doing in the UK. Thank you very much.